So today we are going to realize that in a blast furnace, if thermodynamics fundamental is not well understood by a operator, then really they fail in a disaster, or we can say a catastrophic type of situation may occur. So timely action, reading those signals are very important in order to cope up with the remedial measure. So here we will walk through a forensic autopsy of a catastrophic operational failure. So this is not just a history lesson, it's a survival guidance for any manager or any shop floor manager facing a cooling cycle. So by end of this session, you will gain three critical deliverables. The first, you will learn to identify the uh, early warning signature in the top gas and silicon trend before they become terminal. Second, you will understand the exact mechanics of a how a raft imbalance trigger a hydraulic backlog in the heart. And third, you'll able to implement a proactive recovery strategy, which is very important, that defends the energy balance rather than chasing symptoms. So on the slide, you see our wireframe furnace uh, glowing orange and data point indicating a system under extreme diagnostic scrutiny. So to understand how we lost this furnace, we first have to understand the specific mechanical and chemical design of the machine itself. So now look into this slide number 2. So we are dealing with a mid-size workhouse, a working volume of 953 cubic meter and a hard die of 6.5 meter. You'll notice the cooling system array highlighted by the gray arrows. We have got cast iron steps in the heart transitioning to copper plate and steps as we move up through the Bosch and stack. This furnace utilizes 14 tier and 2 taphole positioned at 90 degree. Our body chemistry noted in the bottom right box is a 100% pellet diet, that is 75% flux and 25% acid, supported by raw material, limestone, dolo, and others fluxes. So the factor here is our heart configuration density. So with two tap holes and a 6.5 meter dia, or margin for the drainage error is incredibly thin. Any significant accumulation of viscous slag will rapidly affect the tap hole's capacity, leading to the structural paralysis we are about to analyze. So this machine is designed to run within various specific steady state target parameters to maintain its thermal equilibrium. So coming to moving forward, so these are our flight coordinates for a healthy campaign. On the top left, we aim for 2364 ton of hot metal per day at a target temperature of 1460 degrees centigrade. Now look at closely the slack dynamics box. Our target melting point is around 1400. The factor here is your survival window, the 69-degree delta between iron temperature and the slag freezing point. Our process input shown in the bottom left include a wind flow of 114,000 almost normal meter cube hour and an a injectant rate of around 60 to 70 kilogram per ton. So note the top gas utilization aim of 50%. So these represent a balanced state where kinetics and thermodynamics are in synchronization. So when your hot metal temperature start drifting towards the 1391 degree, around 1400 and slightly less, you are not just losing quality, you are losing the physical ability to move liquid through the furnace. So despite this clear target, a series of misstep pushed the system across a critical threshold into a total collapse. And further to further we can show those things, especially here in this slide. So this is the point of no return. So the data box on the right represent a total system failure. Our hot metal temperature plummeted below critical 1340 degrees centigrade mark, well below the 1391 degrees slag melting point. Simultaneously, silicon level crashes below zero point 0.1 weight percent. The so what factor is here is the mechanical, not just the chemical, because the internal temperature was lower than the slag liquidus point. The slag physically solidified inside the furnace. So look at the bottom text. 5 blowpipes were completely choked with solidified slag. This is the ultimate operational nightmare. So we didn't just have a cold furnace, we had a physical blockage that prevented the wind from entering the raceway. So when the slag backflow into your blowpipe, the furnace is effectively dead. We are no longer making iron, we are managing a massive mechanical recovery. So this is not happen all at once. The autopsy reveals a clear timeline of early warning that were fundamentally misinterpreted. So the next slide, which is all talking about the timeline of collapse, that is on phase 1. So as you can see, follow the yellow oscillograph line across this slide. So at 1140, the shift team made the catalyst mistake. They reduced oil injection to 6 due to an extreme silicon condition. They were chasing a symptom. By 1938, you see the jagged peak in the timeline. Wind flow was reduced to 96,000 normal meter per hour to control a wild cast. Then at 1955, physical stability was lost with a heavy slipping and hanging detected. The visual boxes highlight this intervention as isolated event, but they are a chain reaction. And so what is the 1140 oil reduction or injectant reduction? Stop the burden of necessary thermal energy. By the time they saw the wild cast at 1938, the hearth was already failing to drain because of increasing viscosity. They treated a drainage problem by cutting wind, which only accelerated the cooling cycle. As the thermal deficit deepened, the intervention became more desperate and the destabilization became terminal. Coming to the timeline of collapse, that is phase number 2. So this is the what a dying furnace looks like on a monitor. At 12:10, they tried a first emergency intervention by adding a double coke charge, a blank following a severe sleep. By 2055 rather, wind was slashed again to 1.17 bar at 2200. In a state of total desperation, the spiked injected to 10.0, but it was too late. Hot metal was already plummeting to 1340 degrees centigrade. Look directly to the furnace situation, which comes to be very alarming. So here the coke blank trap, while adding a coke is necessary, the phase 2 chaos shows that the furnace had already lost its internal structure. The repeated slipping indicate that the cohesive zone had collapsed and alkali accumulation was likely gluing the burden to the wall. So these reactive uncalculated fuel spike and the wind cuts created a violent destabilized raft that the process could no longer absorb. So by 2300, the battle was lost and the team had to initiate the formal final shutdown procedure. And coming to our very important slide on the final shutdown. So look at the red cross section of the hearth on the slide 7. At 2305, the furnace was officially down. The status was terminal hearth critical overfilled, tier level choked, and the slag level at its maximum 6.5 meter level or limit, we can say. So the visual shows the solidified slag filling the blowpipe and the hearth area being completely lost. The physical autopsy report on the right confirmed that the slag runner and the trough were filled to absorb maximum capacity. So this is the loss of the also to the taphole. There is a casting failure due to which taphole is also lost. So when the taphole are lost and the blowpipe are choked, you cannot deliver anything to the furnace. Furnace is become furnace success become helpless. So you are looking at a days of mechanical drilling and manual cleaning just to get the furnace to a state where it might accept a blast. So this is the ultimate price of reactive non-theoretical operation. So to prevent this from ever happening again, we have to look at the diagnostic matrix to see exactly where we miss the mark. So diagnostic matrix, which is also very important, and where we are going to see that where did we miss. So this is our forensic breakdown. So look at the fuel strategy row. The shift team made erratic oil cuts followed by a desperate spike. Theoretically, they should have maintained a raised adiabatic flame temperature or raft equilibrium. So for hot drainage, they cut the wind to manage blowing taffel, but they should have been managing slag viscosity and viscosity before the temperature drop. So finally, look at the stack permeability. They keep the planking with the coke but fail to address the root cause. Alkali accumulation. The so what factor is the gap between the reactive and the theoretical operation. So if you only react to the symptom like a wind, cast, without understanding the uh, underlying craft or viscosity shift, you will almost always choose the wrong lever to pull. So let's dive deeper into the first major miss, the total loss of the thermal balance and the raft control. So coming to the number of misses, and those are the first miss where the thermal imbalance and raft control. So the visual shows the clear plum in orange, but notice the telemetry data below it. So raft dropped to 400 degrees centigrade and the melt rate dropped of 35%. So the analysis text confirmed that the 1140 injectant reduction was the murder weapon. It starved the burden. When they later made reactive wind cut, they fundamentally altered the oxygen to fuel ratio, violently destabilized the. So the operational impact is a catastrophic cooling cycle. So when you drop by 400 degrees centigrade, your melt rate is not just slower, it's insufficient to keep the slag in liquid state. The furnace was robbed of the thermal energy required to process the incoming burden. So you cannot unilaterally cut fuel and expect the thermodynamics of the lower zone to remain stable. So these thermal failure led directly to a chemical crisis in the slag, which destroyed our drainage mechanism. So coming to our miss number two, and miss number two is about the slag chemistry and a hard drainage. So look at the normal versus crisis comparison on the slide 10. In the nominal state on the left, slag flows smoothly at more than 60 degrees centigrade, but on the right, in the crisis state, look at the jagged red mass blocking the flow. As the temperature dropped below 1391, the sub-melt threshold, slag viscosity spiked exponentially. So this is the so what factor. The dense viscous slag could not physically drain through the taphole. So this created a hydraulic backlog that caused the heavy blowing. The operator saw instead of draining out, the slag was pushed backward by the blast pressure, filling the blowpipe. This confirmed that wind casting is often a sign of high viscosity and poor drainage, but just too much wind stack was not also becoming physically paralyzed by the micro impurities. So coming to our next mix, that's the mix number 3, and this is about stack permeability and the alkali. So the visual on the slide 11 shows the internal burden with high friction and blockage icons highlighted in yellow. The repeated slipping at 1955, 2010 and 2154 is the smoking gun or severely degraded stack permeability. So thermal fluctuation likely led to poor pre-reduction and severe alkali accumulation. So as alkali recycle in the stack, they create a glue that prevent the burden from descending smoothly. So the factor here is the total loss of the stock line. When the burden becomes glued and then violently collapse, it destroys the gas distribution and puts out the fire in the hearth with a mass of cold unreduced material. So you must monitor your eta, CO and top gas to ensure the burden is properly pre-reduced before it ever hit the Bosch. So when we synthesize these three mistakes, we see a clear lethal chain reaction that um, uh, led to system stress. So coming to the synthesis part. So here the chain reaction of collapse is shown. As you can see, it started with the erratic fuel adjustment, the catalyst. This led to a destabilized raft and a loss of energy balance. So step 3 is plummeting internal temperature below 1391. Step 4, an exponential spike in slag viscosity and a loss of fluidity. So this causes the severe hearth accumulation, the point where we are unable to drain. Finally, we hit step 6, the slag backflow into the blowpipe, responding final system death. So the operational impact is that each stage of this chain makes the next stage inevitable, and if you don't break the chain at step 1 or 2 by defending your raft, you are virtually guaranteed to end up at step 6. So this is why a day-to-day control is actually a minute by minute battle for thermal equilibrium. So this disaster was avoidable. We have developed 3 proactive control strategies to ensure it never ensure it and never happens again. So what is a better solution? So better solution is nothing but we must have to have a proactive control strategies, especially um, in our departments. So first, raft integrity, you must manage the flame temperature precisely. Never make isolated oil or wind cuts. So always maintain the accumulated oxygen to fuel ratio. Second, pre-reduction monitoring, actively reduce your top gas analysis, specifically eta CO and top gas. Mm, Really, top gas is important and its analysis is very important. It can indicate each and everything regarding hanging, alkali and sleep. So the preventive slag chemistry, where we anticipate the viscosity changes before time. So you must control your slag basicity and monitor the sulfur capacity continuously to guarantee the hearth drainage mechanics before you hit those critical low temperature. So moving from reactive to proactive, if you mm, wait for the wild cast to act, you have already lost the battle. So we box up with the 3 core deliverables or directive that must be defined your future shift operation. So so the lesson that learned from this chapter is that the core directive can be followed, and take these three rules back to pulpit. One, defending the energy balance, the raft equilibrium, and your fuel strategies are the different uh, for different lifeblood of the furnace. So, never make unilateral reactive cut. Two, proactive drainage mechanics. A blast furnace must bleed to survive. So monitoring slag chemistry and uh, slag chemistry and the hearth heat loss in non-negotiable. So these read telemetry, not just the symptom symptom. So erratic wind cuts might mask a wild cast, but they accelerate the underlying thermal collapse. So rely on the your ATACO and theoretical parameters to guide your all the subordinates. And this autopsy was evening just attempt for a operators to awaken them, and this is a sort of a attempt to make them aware. So don't let it to be in vain. Learn the sign, try the theory, and keep the iron flowing.